Is James Stuart Modena, and I am here today to talk to you about the shapes of molecules. I am a DPhil chemist here at the University of Oxford, and just before we really get started, I just want to make sure that everybody has a periodic table so that they can see it, and also something to draw or something to write on, just because there is going to be a little exercise in the middle of this session, just so that you can do your own working, basically. So, to start out with, I would just like to introduce myself a little bit. So, a little bit about me. At secondary school, I was sort of that in-between year where I had both letters and numbers in my grades. So I did triple science, I did history, I did both French and Spanish. Some of you may have noticed that my surname of Stuart Modeno is Spanish, so I did that a little bit earlier because I am Spanish, but I also did further maths and drama as well, and I did quite well in my GCSEs. Moving on from that, I went to sixth form, and at sixth form I did chemistry, maths, and history, doing very well in the sciences. So given that, I sort of thought, okay, well, chemistry really seems to click in my own mind, so I figured I'm good at this, I'm going to follow through with it. So I went and I did my integrated master's course. So immediately starting in 2019, I did a 4-year degree, which I ended with a master's degree at the end rather than a standard bachelor's degree. During this time, I did a couple of different research projects, one of which was between my 3rd and my 4th year, and that was working on CO2 electrochemistry. So rather than just using electricity rather than heat in order to cause chemical reactions to go. And then during my master's year, I focused on what we tend to call low coordinate iron. So using an iron molecule that was very reactive in order to react with carbon monoxide and turn it into useful products. And this is the chemistry that I really started to enjoy. And so I went on to start my PhD, or my DPhil, as we tend to call them here at Oxford. I joined on to something called the OxICFM CDT. So that stands for the Oxford Inorganic Chemistry for Future Manufacturing Centre for Doctoral Training. It's a bit of a mouthful, but in essence, it's just a way of getting funding for the PhD that's a little bit simpler. And the project that I'm working on specifically is about aluminium bimetallics. So aluminium bonded to another molecule, or another metal, I should say, in order to activate small molecules. So things like carbon dioxide or nitrogen or hydrogen, and using those to turn them into useful products. I did mention inorganic chemistry in that. That might be a term that you're unfamiliar with at this stage in your chemistry education. So I just wanted to go over that sometimes chemistry can be split into these 3 different disciplines, those being organic, inorganic, and physical chemistry. There might be a temptation to look at organic and say, okay, that's the biological stuff, but actually that's just referring to sort of carbon-based molecules, carbon-based compounds, which is a slight misnomer. Because although, yes, organic chemists work on a lot of carbon things, I myself also work with a lot of carbon-based molecules. It's just the area that you're particularly interested in, the aspect of the molecule that you're really interested in. So me, as an inorganic chemist, I'm really interested into what the non-carbon atoms are doing in my molecule. So for me, that's my aluminium, and that's my other metal in there. So for me personally, I tend to work with iron, cobalt, and nickel. And so those are the atoms in my molecule that I'm really interested as to what they're doing, how they're reacting, and what their potential uses are. Of course, that leaves physical chemistry. So this is the sort of the physics involved in the chemical properties and the reactions that are going on. So what we're looking at today in terms of the shapes of molecules really encompasses all of them. Okay, so we're going to look at some carbon-based molecules, like some hydrocarbons that you're probably familiar with. We're going to also look at some inorganic molecules, which you are possibly less familiar with. And then we're also going to look at them in terms of their importance, in terms of their shape, because those can have an impact on their physical properties. So that's a nice little intro as to why we care about the shapes of molecules. So far, you're probably having learned molecules that look a little bit like this. They're flat on the screen and you draw them out with sort of 90-degree angles between all of the bonds. So this here being propane. That being said, in reality, molecules exist in 3D. They have a shape to them. And as chemists, we tend to draw this out in this manner, using sort of bold and dashed wedges in order to show the 3D properties. So if we take propane, for example, what you see there, it's got 3 carbons and it's also got 8 hydrogens. In terms of it being 3D, you can see that I've drawn the sort of a hydrogen, carbon, 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 hydrogen with straight bonds. That means that they're in the same plane. So they're all aligned. They're all in one plane. So with you watching this on a screen, imagine that those atoms are all on the sort of flat on the screen, as it were. If they've got a bold wedge coming out, that means that the hydrogen is sort of pushing out. So it's kind of going towards you, as it were, on your screen. It's coming out towards you. And the dashed bonds are going backwards. So sort of into the screen, into the monitor, the computer, whatever it is that you're connected on. And that can actually be really important for us. So for molecules, the shape can tell you about where the electrons are. And really, as chemists, we're interested in electrons, where they are, where they go, what they do. And this can have a lot of impact on many aspects of the molecule, such as their physical properties and also their reactivity. The reactivity being a really crucial one for chemists like myself. So, how do we go about working out what the shape of these different molecules are? So, one way to do it is with this valence shell electron pair repulsion theory, or VSEPR. Hydrocarbon, yes, hydrocarbon is exactly like methane, something that is only carbon and hydrogen. Good question. So, also, yes, please feel free to type a question in the chat. So, VSEPR is how we go from your typical dot and cross diagram, or you may call it a Lewis diagram, into a better 3D representation. So, the basic idea is to get different regions of electron density to be as far apart as possible. This being sort of each area of electron density being either a bond or a lone pair. Is valence shell the outermost shell? Yes, it is. We think about the outermost shell in chemistry because these are the ones that are the most reactive. They're the most available electrons, and so that's where all of the properties of importance come from in chemistry. So, in terms of why this is important for physical space, electrons are negatively charged, and therefore they will repel each other, and that's why we can get different shapes. So I'm going to go through them here. So if you've got a molecule that is, this system is the VSEPR structures, they're the sort of standard way that molecules will, it's the standard way that the geometry of molecules will occur. Why do like charges repel? Why they do that is a physics question, so I will leave that for a physicist to argue with you. Effectively, it comes down to kind of quantum mechanics stuff. If you think about it like a magnet, you can't have two north. If you have two north magnets, they're going to repel each other. It happens similarly with things that are charged, like ions. So electrons have an inherent negative charge, and so they will repel each other. But how do they repel? That would come down to an electrostatics argument, in that they cannot exist in the same area because they have sort of the same intrinsic charge. I hope that answers it. For the sake of this session, we're going to focus on just saying electrons will repel each other, okay? So, the standard structures that you can have. In this case, we say that A is your central atom and X is whatever it is, your area of electron density. So this can be sort of, usually we say that this is what it's bonded to. So if you have a molecule in the middle, so if you have an atom which is bonded to two other things next to it, you can think of this, for example, as CO2. It would come under an AX2 system because the central carbon is bonding to two different oxygen atoms at either end. And in order to get those two CO double bonds as far away from each other, it's going to put them at 180 degrees. And that gives you a linear molecule. You can then have an AX3 system whereby it's bonded to three different things. This is perhaps a little bit more, or is perhaps a little bit less familiar to you at a GCSE level, but in particular, boron containing compounds will tend to make three bonds. And so these will tend to become what we call trigonal planar. Again, everything's in the same plane, so they're all flat in one dimension. So they're all 2D structures, really. But in order to get the electrons as far apart as possible, they'll go to 120 degrees. Things start getting a little bit more complicated once we have four areas of electron density, so an AX4 system. So this is like your methane that we mentioned earlier. And once you've got methane, in order to get the charges to be as far apart as possible, you can't keep them in the same plane. Because in the same plane, you can imagine that they would just be at 90-degree angles. Whereas if you make it tetrahedral, as we call it, with each of the atoms that it's bonded to being one corner of a tetrahedron, that's going to give you the maximum angle around that central atom. And in this case, that being 109.5, roughly. Oh, excuse me. Yeah, roughly 109.5 degrees. There are a couple more systems which would tend to be for more inorganic compounds, those being the AX5 and the AX6 systems. Once you get to this sort of degree, you're dealing with things that are not only things that will have a plane in them, but also axial positions, as we refer to it as. Oh, I'm just going to finish. I've seen a very good question. I'm just going to finish on AX5. So with AX5, in order to keep the electrons as far apart as possible, three of them will go into a plane with the central atom. Each of these will be at 120 degrees. But then two others will need to go above and below that plane. And that's what gives you the sort of the axial positions, which are at 90 degrees to that plane. Then when you move to, we call this a trigonal bipyramidal, by the way, because again, you have the triangle in the plane, which gives you your 120-degree angles. And then the two pyramids are formed by the axial positions, which give you your 90-degree angles. In terms of the AX6 system, whereby they are all at, I don't have a little molecule to show you, unfortunately. But in this case, you can imagine it, you've got a sort of a square like an X, and then you've got it's in 90 positions as well. So we call this an octahedral because every single thing is at a 90-degree angle to each other. Why is it called octahedral when there are six X's and only one A? The reason for that is because when you draw this out in a 3D structure, which I've tried to represent here, it gives more of an octahedral arrangement, as it were. The 3D shape is more octahedral rather than being a hexagonal sort of system, if that makes sense. The additional sort of Z-axis makes it AX, makes it an octahedral rather. Wouldn't electrons be further apart if they go in separate planes in AX3? Interesting question. I'm assuming you mean if you start to deviate one into the sort of Z-axis, for example. By doing that, you'd actually be decreasing the angle between, because with the angles that we're looking at are from the X to the A to the X again. And so if you start to deviate that angle ever so slightly, start to move that X position out of the plane, it's actually decreasing the angle between those different atoms. I'm trying to think if there's an easy way that I could show you. Unfortunately not. Is the AX system like different planes the atoms lie on? No. So the AX system is So to give you an example, sorry, more questions are coming in. Is the AX system like different planes the atoms lie on? No. So the AX system is built on one central atom, being the A, and how many things that is bonding to. So those are the different X things. When I refer to a plane, I mean like, are they all is sort of flat, as you will. So if you can think about an AX3 system, do I have one present? Oh, yes, I kind of do. So if you think about an AX3 system, so this here, this is all in one plane, as in like all of the atoms can be flat with each other. And going back to the question earlier, let's say I try and deviate this bond further around here, you can then see that this bond is now shorter than the 120 that we had earlier. Bond angle. I hope that answers your question. How would AX4 make a triangle? So when I mentioned the triangle, I'm more referring to the different X components in the AX4. So the bottom three, the one that's a straight line, the one that's a dashed line, and the one that's a bold line, those sort of three atoms would go and they would make a triangle on the bottom. And then you have a fourth one above that plane. So if I take this really quick, so you can see here that this is, if you imagine that my fingers are another area of electron density, you've got these three here, which can all lie on one plane. And then you've got this one up here, which makes your tetrahedron. The three are in a triangle because, as you can see, they make a triangle there. It's a tetrahedron once you move into 3D. But a triangle has three sides. Absolutely, yes. Yes, a triangle does have three sides. Just seeing new message. Okay, I hope that clears things up for people. Things can get a little bit more complicated with these systems. Sorry, I can't see the model because of green screening. Okay. Unfortunately, I don't have anything bigger that I could show you other than what is a lone pair. Oh dear. Okay. Lone pair is two electrons that are not involved in bonding. And they're sort of by themselves held onto the central atom, but they're not involved in like a covalent bond. Okay. So yeah. If you do have a lone pair in your molecule on your central atom, they can start to distort the geometry. So we tend to think of, when we're looking at the geometry, we tend to start from the assumption that the lone pair acts as though it's bonding to something in order to give us our geometry. So for example, in ammonia, which is NH3, that central nitrogen has a valence count of 5, and so it wants to form 3 bonds, one to each hydrogen, in order to complete its octet so that it's stable. So 3 of these 5 electrons get taken up in bonding, which leaves 2 left over. Those 2 will pair up and become a lone pair on the nitrogen atom itself. In terms of what that means in terms of its shape, what actually ends up happening is we treat it as a tetrahedral structure. So an AX4, because you've got the 3 bonds and the 1 lone pair, so 3 plus 1 makes 4. And then you start to distort that geometry from there. So lone pairs, because you've just got 2 electrons that are close to the atom and they're not involved in a bond, they will tend to distort the geometry so that those the XAX angle becomes smaller. And so it becomes tighter. And so in ammonia, rather than having 109.5, you'd have 107, I want to say, degrees angles between each of them. So in terms of how we actually go about doing this method for VSEPR, what we do is, he says, with his whiteboard failing him, what we do is we draw out the dot and cross, the Lewis structure of the atom, of the molecule that you're given. Once you have that, you can identify how the electrons are arranged. So whether it's got a lone pair or not, or whether all of those electrons are involved in a bond. You then write it out in your VS-EPR notation, so AX, L, whatever. And then you apply the 3D structure that keeps the electrons as far away as you can. So this is where the AX2, the AX3, the AX5 system come in. And then you can sort of adjust for the lone pairs. I'm not expecting you to know the exact angles for things, or don't worry about that. I just want you to get a general idea of what the different shapes of the molecules are. So here are 8 examples that I am going to ask you to go through. Do not worry if you don't get them all at the minute. What I am going to do is I'm going to start a poll in the chat, and I am going to go through one of these as an example. Okay? So you should be able to see that poll in the chat. So I'd like you to pick one of these that I will go through as an example, and we can work from there. Okay, I'm also going to very quickly switch over so that I can share my... Cool. Okay, so the example that we're running with is P and then C6H5 3. You may hear me refer to this as triphenyl phosphine because this C6H3 group can also sometimes be called phenyl, like that, or just, I might just call it pH. So a phenol group itself this is actually one of the molecules that I asked you to give a quick look at on MolView. Isn't pH the potential for hydrogen? That is spelt with a lowercase p, uppercase h. So yes, you're correct in that we do use pH separately, but this is an abbreviation that we use when we are drawing out our molecules. So the phenol group is basically you will have it like this, and with alternating single and double bonds, CH, 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 C, this, and then whatever. Just remove that really quick. So, in terms of how this is bonding to your central phosphorus, because the first one is always going to be our central atom, we put the central atom in the middle when we're doing our Lewis structures. Now, I know that phosphorus is just below nitrogen, so phosphorus is going to want to have 5 electrons as standard. So in order to complete its octet, it's going to want to form 3 bonds. You can see that this carbon here is already forming a double bond and a single bond, and this here is another 1 single bond. So for the sake of this example, I'm going to put in 3 pHs that each have 1 electron that they want to share with the phosphorus. This phosphorus center is then going to complete that bond with each one of these, which is giving up. So that's taken 5 of its normal electrons and given away 3, which gives us another 2 that just have to pair up like this. So this is the type of Lewis structure that we end up getting with 3 bonds and a lone pair. So in terms of our VS-EPR notation, what we have here is an AX3L1 system. You have the three X's here, here, and here. I go to the X's, and you have the one lone pair. I'll just remove some of those arrows because they might get a little bit confusing in a second. Okay, so you have an AX3L1 system. As we mentioned earlier on when dealing with lone pairs, so we have a 3 plus 1, which gives us our 4. So we're looking at some sort of tetrahedral arrangement of them. So if I just quickly scroll down just to give myself a little bit more space, whoop, like that. What we'll end up having is we'll have the central phosphorus with, with one straight bond in here. I'll put in one dashed bond and one wedged bond. So we end up with a system like that, which kind of looks like your tetrahedral up here. I've just purely by accident flipped it. Now, normally in the AX system, we'd have another thing up here, but this is where we have our lone pair. So which we can normally draw rather than being in a bond, we just draw a sort of balloon around it like that. And so these angles would normally be 109.5 because it's in a sort of tetrahedral AX4 type system, but they actually get a bit reduced down. So they tend to be, for triphenylphosphine, I believe it's about 105 degrees because of the effect of this lone pair. Does that make sense for people? Or would you like me to go through another example? Another one, sure. So what other thing will we go through for an example? Let's go through PCl5. Okay. So PCl5. Again, so we're dealing with phosphorus, which phosphorus is in group 5 on your periodic table. Okay? That means that it has 5 electrons that it wants to form. Fluorine is in group 7 on your periodic table, which means that it is phosphorus dangerous. It can be. I would, sorry, this is an aside that I will go through afterwards. Sorry, I will get through this example and then I'll come back to a question. So chlorine is in group 7 and therefore it has 7 electrons. So in order to complete its octet, this one would need 1 electron. Phosphorus would normally need 3 electrons to reach 8. But you can see in this example that this has got the phosphorus bonding to 5 chlorine centers. And this is something that's called expanding the octet. So some elements that are below the second row, so below carbon's row, they can expand their octet. Okay, it's just a feature that they can do because some of their orbitals are more available. So we're going to focus on the chlorines. They each want 1 electron. So each one of these chlorines wants 1 electron bonding, and I will just quickly show this sort of structure is around each chlorine. So you can see that they've each got 3 lone pairs around it. What is the thing above the P? I'm assuming that you mean this here. This here is a lone pair. Okay, so these are 2 electrons that are not involved in bonding. Okay, so going back to our PCl5 example, you have the central phosphorus, and you have 5 chlorines around it. Each one of these chlorines wants to get 1 electron in order to form a single bond. Luckily, phosphorus has 5 electrons that it can give away. So it can give 1 electron to each chlorine, like so. Okay? And what that gives us is that gives us an AX5 system. Okay? Now, if you go back and you can just about see it up here, the trigonal bipyramidal system here. So what that means is that we're going to put phosphorus with 3 chlorines in a plane like that. And then you also have 1 above that plane and 1 below that plane. Isn't it possible for there to be 8 electrons in the outer shell? So that is true for the first row. That's what we call filling the octet. You might have heard me say that a couple of times. It's only true for the sort of first row. Once you get lower down, you can start expanding it, and therefore you start filling up you start filling up orbitals that would normally be unavailable. So you're half right, half wrong in terms of you can only have 8 electrons in the outer shell. How do you know which plane to put them in? For the sake of this example, it doesn't really matter. In fact, there's an argument to be made that each one of these chlorine atoms is in solution, they're constantly swapping. So in terms of how do you know which plane to put them in, this is just the arrangement that puts the electrons as far apart as possible. Are they spectator electrons, referring to lone pairs? Yes. So I'm trying to remember the naming system that you may use at GCSE. I think that yes, you could refer to them as spectator electrons because they're not involved in bonding. Do you just need to memorize that? In terms of the sort of structures, I'm going to leave those up for you. So you can absolutely keep looking at these structures. Once you get to sort of, if you're interested in chemistry and want to continue with it, you don't necessarily need to memorize them. It will become a bit of second nature. So something that you just know intrinsically. So do you just need to memorize it? Yes and no. Does the PCl5 example make sense? Yes, perfect. So there are a couple of others up here that I would like you to have a go at, those being these ones here. So you've got your methane, your CO2, your carbonate ion, a triiodide ion, SF4 and SF6. I'd like to give you guys a little bit of time to have a go at some of these now. If there's not enough time to look at them in the session, feel free to have a look at them afterwards, and you can easily look up these answers online. Yeah, we'll let's say, give you 5 minutes just to try and work through some of it. And I'll go through, yeah, I'll start going through some of them in about 5 minutes. Sorry, could you explain this again? I don't get it. Okay. How to explain this again in a different way so that hopefully you might better understand it. By the way, feel free to mute me if my voice is going to become annoying as you're trying to work through this. Just, make sure to come back at 10 past. So, in terms of going through this again, the VSEPR theory relies on the Lewis structure. So that is this sort of structure here. Okay. It also relies on you being able to look at the periodic table and understand how many electrons there are and how many it wants in order to become stable. So in this example, the phosphorus here in the middle, it naturally has, it's in group 5, and so it will have 5 electrons around it. I've drawn these as dots or filled in circles. Okay. It's bonded to 3 things because I've given you P, it's PPH3. Okay, so it's bonding to 3 things. Each one of these wants to form one single bond. Okay, so it's forming a covalent bond. So each one of these pHs is giving 1 electron and accepting 1 electron to and from that central phosphorus. Okay, by doing that for each of them, this phosphorus gives up 3 electrons and accepts 3 electrons, but that still leaves 2 electrons that it would normally have in a non-bonding state. Okay, they have nowhere else to go but to pair up with each other and become what we would call a lone pair or a spectator electron in this case. Okay, because therefore you have 3 things that the phosphorus is bonding to. You have an X3 and you have 1 lone pair, so you have an L1. That 3 and that 1 gives you 4, so you have a tetrahedral system starting at AX4. So you make each one of the X's a pH, but that still leaves you with that 1 vacant space for the lone pair to go. Okay, and so that lone pair will just occupy that extra space, and it will push the angles of the pH angle. So it's sort of this angle here, and it will push this to be smaller. I hope that explains what I wanted to say. Would double bonds work the exact same way? So the shape of molecules is to do with the areas of electron density. So for the sake of VSEPR, yes, a double bond acts in the same way that a single bond would. I hope that answers your question as well. Right. It is, I'm going to say that we're going to have we'll give another couple of minutes on this. Does the VSEPR model work for any molecule? No, and spoiler alert, we're coming to that in a little bit. It works for a lot of them, but what's VSEPR? This is VSEPR. This theory that I'm telling you about here. Valence shell electron pair repulsion. Basically, in your valence shell, the electrons will repel each other. And that's how we can come up with the shapes of the molecules that we're dealing with here. So VSEPR stands for valence shell electron repulsion electron pair repulsion. If I can remember to write properly, electron pair repulsion. Is this part of A-level chemistry? I believe that VSEPR is a part of A-level chemistry. I believe. I'm not 100% sure on that. I think it might depend slightly on your exam board. Yeah, I think it might depend slightly on your exam board. It's certainly something that gets covered in the first year of an undergraduate course in chemistry. But I believe it is also covered in A level. Okay. Right. What I'm going to do here is what's the difference in the structure of an ion, for example, CO3 minus, oh, CO3 1 minus. CO3 1 minus? Okay, 2 minus. Okay. We can go through that as one of the examples. I'm not going to have time to go through all of them. So the examples that I will go through the CO3 2 minus as one of the examples. Yeah. Okay. I'll give everybody one last minute to finish up any work that you're doing. And I will very quickly put up a poll. Right, yeah. Right. I've just launched a poll that can which molecules do you want me to go through? You can submit multiple if there's ones in particular that you would like me to have a look at. I'm not going to have enough time to go through all of them because there is one thing that I do very much want to show you before we leave today. So okay, the looks of it are the two most popular are CH4 and CO3 2 minus. So I will go through those now. So we'll start with CH4, which is methane. So carbon, I know, is in group 4. So it will normally have 4 electrons. I will write electrons as E minus, by the way. Electrons. Hydrogen is in group 1. It has 1 electron, but it only wants, this will want 1 electron, whereas carbon will want another 4 electrons. Okay, so methane is going to be using covalent bonds. So with the carbon in the middle here, I'm just going to draw out the hydrogens around each of it. So each hydrogen is going to have 1 electron that it wants to share with the carbon. That's what makes it a covalent bond. These electrons are being shared, not fully donated. And the carbon is going to want to share its 4 electrons. So it's going to put one here, one here, one here, and one here. That way, all of the atoms in here are happy. Each hydrogen has got 2 electrons around it, like that, 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 and that. And the carbon has got 8 all around it. Okay? Now, what this means is that we have an AX4 system. You have A being your carbon here, X being each one of your hydrogens. Therefore, we can say that methane is going to be tetrahedral. Tetrahedral. Okay, so we start with our carbon in the middle. We draw 1 straight bond, 2 straight bonds, those being in the same plane as each other. But then in order to make it tetrahedral, to give it that 3D-ness, we will draw 1 dashed bond. That means that it's going back into the screen of the paper, or into the screen, sorry, and 1 wedged bond, like that. That's the one that's coming out towards you. The other one that we're going to work on today is carbonate, so CO3 2-. So again, carbon wants 4 electrons around it. Each oxygen is going to behave slightly differently, so we'll have a look at this separately. So we start by drawing in our carbon in the middle, and then we'll draw, 3 oxygens around it, like so. Each oxygen is in group 6. So it will have 6 electrons, and it will want 2. Okay. Carbon is, what's the 2- for? So the 2- means that it is negatively charged. I will come on to that very quickly. So carbon is group 4, has 4 electrons, and it wants 4 electrons. The 2- means that it is negatively charged, twice, in fact, negatively charged times by 2. What this actually means is we have an extra 2 electrons present. Okay, so if I start out at the carbon this time, so if I say carbon has got 1, 2, 3, these are going towards the oxygens. In order to make the carbon happy, we're actually going to need to make one of these into a double bond, like this. Okay, so this is therefore, this oxygen is going to have 1, 2, 3, 4, 5, 6 electrons as normal, plus these 2 means that this oxygen is then going to be happy. Okay, this oxygen has now got all 8 of its electrons. It's good. These other 2 oxygens, however, they can only make a single bond with the carbon. Okay, leaves 1, 2, 3, 6, 7. 1, 2, 7. Okay, so this might be a little bit too far out to make out clearly. So around each of these oxygens, they're forming one single bond to carbon, so they're sharing one of their electrons and they're receiving one of their electrons from the carbon, but that only makes it up to 7. And so this is going to be really, really unhappy in its current structure. Luckily, we have an extra 2 electrons, which in this case, I would just show as circles like that and like that. With those extra 2 electrons, 2-, this is actually now going to be happy because every single atom here has got 8 electrons shared with it. The carbon has got 2 from this oxygen double bond, 1 from there, 1 from here, and has 4 normally. So 4 plus 2 plus 1 plus 1 gives you 8. This one here has got 6 normally, plus the 2 from the double bond, 8, it's happy. These 2 over here and here, where do the extra 2 electrons come from? That's because it's an ion. So this is a 2- ion. So for example, this could be from 2 different sodium plus atoms, because those will be involved in ionic bonding. Anyway, so each one of these oxygens here has 6 normally, plus the 1 shared from the carbon, plus 1 from the extra electron that's around. Now, in this case, what we have here is something that you could probably draw like this. The negative charge on each of these. That negative charge is just saying that that's where the extra electron is. So in this case, this becomes an AX3 system, okay? Because we deal with the double bond in the same way that we deal with the single bond. So we just say that it's all the same. So we get an AX3 system, which is trigonal planar. Therefore, we have 120 degrees. I hope that makes sense. This is where we were at. So, it was mentioned earlier on, does this work for all molecules? Unfortunately, it doesn't. In particular, when you're dealing with a transition metal. So these are things like iron, cobalt, nickel, that lower rectangle in the middle of the periodic table. That's where the VSEPR really starts not to work. Now, this is where I could start talking about quantum mechanics and orbitals and giving you a bit of a look beyond just the sort of shells that you have learned about so far. But we are quickly running out of time. Those things are a topic for A-level and possibly beyond. And I'm a synthetic chemist. I like doing the reactions. I like doing the reactions. Why does it not work for transition metals? That's because I will try and answer this as we go through this next bit. So, hello everybody, this is a reaction that I recorded on Monday. This is cobalt-2 chloride hexahydrate, this pink molecule in the corner. I'm quickly adding this to my round bottom flask. The reason why it doesn't work for transition metals is because they are more dependent on their orbitals. So the areas where the electron densities are more based on that. And I'm trying to not go into this in too much detail because it is a bit too far and I think I might start to lose people. So we'll focus on the experiment being done here. What's the pink stuff? So the pink stuff is cobalt hexahydrate chloride. So it's COCl2 with 6 waters around it. So you can see up here, it's an octahedral thing with 6 waters around it, and it's a 2+ ion, which is balanced out by 2 Cl- ions. So right now, this pink stuff is being dissolved just in water. So as you can see there, and it makes this nice sort of reddy pink color. Take a quick drink of water. It's vibrant pink color. Yes, thank you, me from Monday. Ta-da. Looks like Kool-Aid. Please don't drink it. I cannot stress that enough. What I'm now measuring out is I am measuring out some hydrochloric acid. Is it toxic? It's certainly not good for you. Let's put it that way. The general rule of thumb in the lab is it's probably toxic. It's not radioactive, but it's probably toxic. What you can see here is I'm now adding HCl to this cobalt chloride hexahydrate, and I'm just checking its temperature there. What you can see is that that pink color is quickly being replaced by a very dark blue color. That was concentrated HCl, I should add. That was why I was checking the temperature, because adding acid and water together can make things very hot. But as you can see, as I swirl it, you can see the nice blue color. Yes, it's rather nice blue. The reason why it's turning to this rather nice blue color is because as I've added the HCl, I'm increasing the concentration of chloride ions, those Cl- ions, and those start to bond onto the cobalt center instead of the water molecules. However, because it's a transition metal, that geometry can change. And it's that change in geometry from going from having an octahedral setup with 6 waters around it to being a tetrahedral setup with 4 chlorines around it, that's what gives you the really big color change. And because it's in equilibrium, by adding in water, you can actually push it back the other way forward. What's the liquid for? The liquid is so that you can very clearly see what's going on. If it was just a solid, it would be much harder to see. Here you can see I'm just adding in more water, and you can kind of see it there. The pink color is returning. Is it reversible? Yes, that is what I'm showing you here. I think I put in a little bit more water in order to get it fully back. The idea is that by altering the concentration of the chloride ions, you can change what is directly bonding onto your cobalt center. That changes the geometry around it. That changes the shape, the color. So as you can see here, we got back to our very nice pink. And this process is also reversible the other way. How does it go back to pink? Because I added in more water, there's more water just sort of floating around the cobalt, and therefore the chlorides get dispersed out so that because they're in a solution, they get dissolved out. So you can imagine it as that being that. So those sort of cobalt and those chlorides are no longer bonded onto the cobalt, and so it changes the color back. I am going to quickly run through because that was a lot of chemistry. So let's all just take a breath. Okay? As you breathe in, the oxygen goes into your lungs, and then into the hemoglobin in your blood. It looks a little bit like that. The O2 will react with one of the ion centers in your hemoglobin, turning from ion 2 to ion 3. That introduces a change of shape. The ion actually becomes smaller, and so it can go up and fit into this pocket of the nitrogens. And by going up into this pocket like this, it pulls on this structure down here, which is part of the protein, which makes it more available for other iron atoms in your blood to also take up oxygen for oxygen binding. So congratulations, changing the shape of molecules has been really important, and you've been doing it this entire time. Thank you very much for listening. If you have any questions, please put them in now.